Okay, I think we can start now. Thanks for coming along to this talk just after lunch. For those who don't know me, I'm Daniel Berrange, and I've been working for about 10 years on virtualization, on Libvirt, Xen, KVM, and most recently OpenStack. Today I'm going to talk a bit about work I've been doing over the past year on QEMU to improve the security of QEMU from the point of view of the host and internal network management stack. So we're specifically not talking about security of the guest ABI, which was what the previous talk in this room was about. We're focusing exclusively on the host side security. And I'm going to talk about providing secrets, as in passwords or keys to QEMU, about encryption of data at rest and data in transit, and on authorization of network access. So just to set the scene, this diagram is an exceedingly simplified view of a small part of the OpenStack infrastructure. So we typically have a number of compute hosts running multiple VMs on the hosts. And if you're doing live migration, you'll have a migration data channel between two QEMUs on two hosts. And if you're doing block migration, you'll also have a NBD network connection between the two hosts. You probably have a network connection to your storage, whether it's iSCSI, RBD, or NFS, or some other network-based storage. RBD is the most popular in OpenStack land. And from the point of view of actually interacting with the guest, the tenant user on the internet connects over WebSockets proxies to a VNC proxy server or a serial console proxy, and then that forwards data on to QEMU on QEMU's VNC server or serial console server. And the problem we're trying to attack is that all of these network connections on the internal LAN, they're all going in clear text currently. There's no encryption whatsoever. So if any adversary gets onto the internal network of the cloud, they basically have a very easy time to compromise or access data that's flowing between the different components. So that's kind of the goal of what I've been working to address. So the first thing I'd like to talk about is a little bit of infrastructure that we had to deal with before we got to the real meaty stuff. QEMU has never really had a good way to provide its secrets. People have kind of done it on an ad hoc basis. So, for example, the RBD configuration just takes a password on the command line in clear text, so anyone running PS on the machine can see that password. For disk encryption, we've had to provide a password out of band via the QEMU monitor, and this has created all sorts of pain for the internal QEMU block infrastructure to have to wait for the password to be provided before it can set things up. Or we've even had stuff which just prompts interactively on the console, which is mostly useless for people wanting to automate management of QEMU. So it's complex for management applications and it's complex for QEMU maintainers. So we decided the first thing we need to do is provide a standardized way of getting secret tokens or passwords, whatever you want to call them, into QEMU. So we created this secret object type, and you can provide the secret in either raw format or base64 encoding, and you can provide it either inline as a property on the object or indirectly via a file on disk. And the secret data itself can be in clear text or it can be encrypted with a master key, which you then provide to QEMU separately. And we've got this wired up for the RBD driver, the iSCSI driver, the curl block driver, the recent Lux driver, and also for X509 certificates, well, rather the private key associated with the certificate. It's nice to be able to encrypt those private keys as well. From the point of view of actually using this, there's kind of two approaches. You can either provide the secrets directly for each thing you're configuring inline and encrypted, or you can have one master secret you provide to QEMU, and then you encrypt all of the individual secrets with that master secret. So I've got a few examples here of how you would configure this in QEMU. The first example is totally insecure. You don't want to do this except in development. It just passes the secret data as a field on the command line. The second option is you pass the secret, you create a text file, put the secret data in that file, and just pass QEMU the file name. And assuming the file permissions are suitably restrictive, then that's secure. The file can be in plain text, or it can be in base64 format if that's more convenient for your management application. But what we're actually doing in Libvirt when we use this feature is that we create a single master secret, which we provide to QEMU via a file when you first start QEMU. And then for everything else after that, we provide the secret as encrypted data inline. So you just have to tell QEMU what the ID of the master secret is, and the ciphertext and the initialization vector, and then QEMU can decrypt the secret for that object. And the benefit of doing this is that you don't have to create lots and lots of files on disk for each password you need to give QEMU. You just have one file on disk, and then everything else can be provided inline. So it kind of simplifies life for the management applications. So once you've defined the secret and loaded it into QEMU, you've got to be able to associate the secret with the thing you're configuring. So the RBD server, for example, when QEMU authenticates with RBD, it has to provide a password. So we've got a new property for the RBD configuration, password secret, where you just provide the ID of the secret, which has the RBD password in it. And a similar kind of idea applies for the TLS private key. Slightly different property name here. But again, you're just providing a reference to the secret object, so QEMU can go and grab the secret that it needs for that particular thing that it's configuring. So this has provided us a nice, flexible way of getting passwords, keys, passphrases into QEMU in a secure manner that's standardized across everything QEMU does. The next thing I want to talk about is the TLS encryption. Many, many years ago, I added support for TLS encryption in the VNC server. And when we did that, the code for handling all of this was just all in the VNC server code inside QEMU, so it wasn't really reusable. So we extracted all of that code into another standalone object called the TLS credentials object. And there's two of these objects that you can use. One provides anonymous credentials. You don't really want to use this because it's pretty much useless from a security point of view, but we just needed to provide this for backwards compatibility with the existing features in the VNC server. But the one you want to be using is the X509 certificates. And when you configure this, you provide a path to a directory which contains the certificate files and the private key. And when you're configuring these credentials, you can say whether these credentials will require a client certificate as well. So normally when a network client connects to a TLS server, the client verifies the server identity, but it's less common for the server to verify the client identity. But that's something we kind of want to do in a lot of deployments of QEMU. So there's the ability to tell QEMU to mandate a client certificate so that you can get mutual authentication in both directions. I mentioned on the previous slide that you can now tell QEMU, you can now give QEMU a private key that's encrypted, so you don't have to have your private keys lying around in plain text on disk. And most recently, in this forthcoming release, you can now set the cipher priority. So there's ever-changing guidance on what are the best cryptographic ciphers and modes to use with TLS. So no single hard-coded default is suitable for all. So we can now configure that as needed without having to do any code changes. If anyone's deployed services with TLS encryption or tried to debug problems using them, you'll find that it's a horrific thing to debug. You generally just get an error message saying the handshake failed and no further information at all. And unless you really know a decent amount about TLS and X509 certificates, the chances of debugging it is quite low, and it's a bit hit or miss. So in this new certificate handling code in QEMU, we added some sanity checking. So when you load the certificates into QEMU, it'll do a number of checks on the certificates. It'll make sure various basic constraints are set in the certificates metadata, which are things that QEMU wants to have set. It'll check the key purpose and key usage values that have been declared, because again, QEMU has some predefined requirements for what it expects, and if you don't get those right, then your session's going to fail to handshake. It checks the stupid things like expiry time and validity time, which a surprising number of people will accidentally get that wrong. And of course, it also checks the certificate chain to make sure that the certificate authority you've given QEMU is the same as the one that's actually signed the certificates you've given QEMU, because if you don't get those matching, then you're not going to have much success. So the new TLS object framework was added in QEMU 2.5. We converted over the VNC server in that release. In the 2.6 release of QEMU, we added support for using TLS with the character device backends. So that's used with typically the serial ports in QEMU. We also added it to the NBD server. We worked with the NBD maintainers and got an enhancement to the NBD protocol specification for how to use TLS in combination with NBD. And then we implemented that protocol enhancement in QEMU. And we also implemented it in another NBD server just so that we can verify interoperability. And most recently, in this forthcoming release, we finally got support for TLS encryption with migration. So when the guest RAM contents is being transferred from one host to the other, the RAM isn't all there in plain text for anyone to see. So when configuring TLS certificates, there's kind of a couple of different ways you can go about this. And the way you want to choose depends on your deployment scenarios, really. You could just have one set of TLS certificates for the entire host. So VNC, serial console, migration all use the same certificates. Or you might have different, you might want to give different certificates to different services. So the VNC server and serial console might want to have one set of credentials, and the migration and NBD server might want to have a different set of TLS credentials. So you can flexibly choose which model you want. Or you might want to choose the credentials based on which network the service is listening on. So there's quite a bit of flexibility there for how you configure the TLS credentials with each network service in QEMU. The thing I've been working on most recently in this, over the past, well, it's been 6 to 12 months, in fact, is disk encryption. There's kind of two goals with the disk encryption for QEMU. The kind of threat model is that the person who is administrating the compute hosts that are running QEMU might not be the same as the people who are looking after the storage servers. And one group of people might not trust the other group of people. So the compute host administrators don't want the storage administrators to be able to compromise any of the user's data from their VMs. So there's a clear need to have some kind of disk encryption in play here. Now you might say, well, the guest OS can do disk encryption already, so why do we need it in the QEMU side? That's true to some extent, but doing disk encryption inside the guest has a few downsides. First, you've got the problem of how do you provide the key for the virtual machine? How do you provide the key to the virtual machine when it boots up? Because typically on a physical machine, you'd be entering a password when it boots, and if you've got hundreds of VMs running, you don't want to have someone manually enter a password in the VM console every time they boot. I mean, this happened to me just yesterday. In fact, my hosting provider had their host go down and rebooted my VM, and my VM was dead until I went in and entered the Lux password at the boot prompt. So it's kind of inconvenient. It's a kind of a virtualization-specific problem is, in a cloud environment at least, it's quite common to upload a pre-built disk image and then spawn multiple virtual machines from that same disk image. If you're doing the encryption inside the guest OS, all of those VMs you boot are going to be using the same Lux encryption password for encrypting the payload data, and that's generally undesirable from a security point of view. You don't want to have multiple VMs all with the same decryption key for their disk. So that's the only way to get around that is you'd have to re-encrypt the guest disk image each time you booted a new VM from that same single image. And that's kind of a time penalty you don't want to pay when you're booting new VM instances. And also, as a hosting provider, you might want to have some strong guarantees about the security of your customers' data. You don't want, as a business, you don't want to have the risk that some of your customers' data gets leaked if you get compromised in some way. So you don't want to necessarily rely on the customer to have provided encryption for their VM disk images. You want to guarantee that all VMs running in your hosting environment have got disk encryption, regardless of whether the user thought to turn it on themselves, just to protect you against compromise of your infrastructure. So there's a compelling need to have disk encryption in QEMU itself. This, in fact, already existed for many, many years. If you've looked at the QCOW disk image format in any kind of close detail, you might have noticed that it has an encryption facility. And this sounded like a really great idea at the time it was written. But fast forward a couple of years, and people with some cryptographic knowledge actually looked at this and found that it was lacking in quite a number of ways. For a start, the QCOW2 encryption is hard-coded to use the AES encryption cipher in CBC mode with a plain 64 algorithm for generating initialization vectors, and this is quite an undesirable configuration because it allows a number of attacks on the content of the disk image, specifically a watermarking attack. That wouldn't have been the end of the world if you could configure the algorithms that QCOW2 used, but in another great bit of design, the choice of encryption modes was completely hard-coded, so there's no ability to change these in QCOW2 without breaking compatibility with previous QEMUs. And the other really undesirable factor is that the decryption password you gave to QCOW2 is directly used to encrypt the payload of the disk. So if you want to change the password that you used for your QCOW2 image, that means re-encrypting the entire payload of your disk, which is just not something you want to be doing, really. And that also means that if you come to delete, you want to delete the disk, or if the password has been compromised, then it means you've got no easy way to protect the data. You've got to actually overwrite all of the data blocks to prevent any of them being decrypted. Whereas if you know a little bit about the LUKS format, they don't directly encrypt the payload with the user password, and the password is just used to unlock a master key. So in the event of your user password being compromised in LUKS, you can change the password, and it doesn't have to re-encrypt the entire payload. And you can just destroy the LUKS header, and that makes the entire payload inaccessible. So you don't have to worry about overwriting the entire payload with LUKS. So for all of these reasons why the QCOW2 code is horrible, we decided to deprecate it in the 2.3 release. And then, as luck would have it, we accidentally broke it completely in the 2.4 release. And we got until about a month ago when we realized this. And so we've had 2.4, 2.5, and 2.6 out there, where we had completely broken the QCOW2 encryption such that no one could use it. And no one complained. So evidently no one was using this, which was good because it's horrifically insecure. So we finally actually, despite it being broken, we've now explicitly blocked it in the forthcoming 2.7 release. So even if you wanted to use it, you now can't use it. So if in the very unlikely event you have any QCOW2 images which are encrypted, you have to use QEMU image or QEMU MBD to liberate the data into a better format. And that better format is, of course, going to be LUKS. So as I said, we need to have some encryption support in QEMU. We knew the existing scheme was terribly badly designed. We didn't really fancy inventing our own disk encryption format because getting that right is not a trivial thing. So it's much better to take a format that already exists, has been peer-reviewed over many years, has been studied, its weaknesses and strengths are well understood. So we picked the LUKS format and implemented a block driver for this in QEMU. The reason we decided to implement a block driver in QEMU itself, as opposed to just telling QEMU to use a LUKS volume exposed by the kernel, is all around simplicity of management. QEMU, you typically want QEMU to run without admin privileges. And setting up and tearing down LUKS volumes using crypt setup and dencrypt requires admin privileges on your host. If you've got the LUKS driver works over block devices, and if you've got plain files you want to use it with, you'd have to first set up a loopback device or use QEMU MBD to turn that QCOW file into a block device, and then layer LUKS over the top of it. So that just adds more layers of complexity in the stack and more things to go wrong when you're setting up QEMU. And of course, all that would be Linux specific. So if you wanted to use QEMU on BSD or OS X or Windows or whatever, you'd be locked out of using the encryption. So there were quite a few reasons why we wanted to have LUKS support in QEMU natively. So as I say, I wrote a driver for this in QEMU. It's merged and it's available in the 2.6 release of QEMU. It's interoperable, of course, with the kernel dencrypt and crypt setup tools. And we've actually written a test suite to guarantee that. So we've got tests that format a volume using QEMU and then read and write and open it with the kernel, and format a volume with the kernel and then read and write it with QEMU to make sure we've got interoperability in both directions. The QEMU driver can, of course, be used if QEMU is running unprivileged. You don't need to run any privileged setup steps. It works on any platform that QEMU works on. The QEMU block layer has quite a nice test suite along with it. There's 30 or 40 odd different test scenarios that you can set up to run across any QEMU block driver. So we've got the vast majority of those working with the Lux driver to prove that it's working on all the different scenarios that QEMU block drivers are expected to work under. So I said that stuff was all available in the 2.6 release of QEMU. The work isn't finished. There's more things we want to do. That was basically the first stepping stone. When QEMU formats Lux volumes, it's just hard-coded to always use the first key slot. If you know anything about Lux, you can have up to 8 key slots with different passwords for each key slot. So we'd like to be able to let QEMU manage the keys in each key slot. We want to be able to do secure deletion of disk images, so that when you delete a volume, you don't want to leave the Lux header there, because if someone can recover that volume, they can potentially brute force the user passphrase that's used to unlock the master key. So when you want to delete a VM disk image, you really want to overwrite the Lux header at the very least. So we want to add some kind of facility in QEMU to let you do that overwriting in some kind of manner. We haven't decided what that would look like exactly yet. We want to be able to integrate this directly with QCOW2, so that when you have a QCOW2 image, you can determine that it's actually encrypted with Lux automatically and set up the right decryption structures, so the management app doesn't have the burden of remembering whether this particular image is encrypted or not. We should be able to record whether that's encrypted and just do the right thing. There's already a number of tunables when you're formatting Lux volumes with QEMU. You can set the encryption cipher, the encryption mode, the initialization vector algorithm. But there's a few more things we want to make configurable. In particular, the algorithm that's used for encrypting the master password with the user's passphrase, which is known as PBKDF2. You want to be able to configure the running time of that algorithm by setting the number of iterations it does. As computers get faster at doing cryptographic hashes and so forth, you need to be able to increase the complexity of the PBKDF algorithm. Lux, normally the Lux encryption header is just a 1 megabyte block at the start of a volume. There is actually the ability to have the header in a completely separate volume. The kernel supports that, so for the sake of interoperability, we want to be able to support that in QEMU as well. So we need to be able to point at the separate header volume. So far, the work has all been about getting it functionally enabled. We haven't really focused too much on performance testing and optimization. So obviously, it's all very well having this ability to use Lux inside QEMU, but if it's a lot slower than the kernel implementation, no one's going to use that. So we need to do some work on benchmarking to see exactly how it compares with the kernel implementation, and depending on the results of that, do performance optimization to make sure it's within the same ballpark as using the kernel Lux encryption features. So I just want to give a few examples of how you actually use the Lux support in QEMU. First of all, you need to be able to pass the passphrase for the Lux volume to QEMU. If you remember at the start of this talk, I mentioned the QEMU secrets facility. Well, to provide the password, you need to define a secret object, and in this case, I'm showing how you provide the passphrase via a base64 encoded file. Then, using the QEMU image tool, the create command that you'll know about already. You have to provide the ID of the secret that has the password, and tell it that you want to create a LUKS encrypted format image, and then just the file name and the disk size. And this will create you a plain file that's using the LUKS encryption format, using the default parameters, which we've chosen to be AES-256, the XTS cipher mode, and the plain 64 initialization vector algorithm. Those defaults were chosen to match the current defaults that are used in RHEL and Fedora. But we don't guarantee we'll keep those defaults as the defaults forever. So if you want to have specific characteristics for the encryption options, when you're using QEMU image, you can say you want a particular cipher mode, a particular initialization vector generator, and a particular cipher algorithm, although I haven't shown that one here. So this just shows how you use the option string to configure the different crypto parameters. The LUKS supporting QEMU can be layered over any QEMU block driver, so not just plain files. So in this example, I'm showing how you can use an RBD network volume, and you can format that using LUKS. It's not very difficult at all. It's the normal RBD URI-like format for the file name, and then you just say you want the LUKS format, and that's the password you want to encrypt it with. So that's all very straightforward. As I mentioned, we want to integrate this natively into QCAR2. Currently, if you set encryption equals on, it uses the horribly broken encryption method that we've now disabled. We want to update that so that if you specify encryption equals on, it will use the LUKS format instead. And probably get to that in the 2.8 release of QEMU, if all goes to plan. So that's how to create volumes. How do you actually launch a VM using that volume? Again, the first thing you have to do is provide QEMU with the passphrase for that LUKS volume using the secrets mechanism. Then, using the existing drive option, you have to specify the driver as LUKS, the ID of the secret object you created, and then the file name to the image. And that's about it. So it's slightly more complicated than the non-encrypted case, but not very much. And using RBD volumes, it's much the same kind of thing. You again, in this case, we've actually got two passwords provided, because we're first providing the decryption key for the LUKS volume, and then providing the password to authenticate with the RBD server. But that's just the only slight difference here, really. So that's it about the LUKS format today. It's out there in QEMU 2.6. It's usable. It should be interoperable with the kernel. So that's broadly ready for use. There's support being worked on in Libvirt. The release of Libvirt last month introduced support for LUKS with plain files, and there's work in progress to extend that to cover other disk formats like RBD. So the rest of that will be available in Libvirt in the near future, and then the intention is to also wire that up into OpenStack to start getting encryption of the different storage drivers in OpenStack. So the last thing I want to talk about is access control. I mentioned earlier about the way we've enabled TLS for the VNC server, the migration data channel, the MVD data channel, and serial console. Having TLS encryption is great, but if anyone can connect to your VNC server, TLS encryption on its own doesn't really do very much for you. So you want to be able to have some kind of access control over who can actually connect in the first place. At its simplest, you can do this using the X509 certificates. If you tell QEMU to require a client certificate, and you create a subordinate certificate authority for each service you want to have different access rules for, then you can tell QEMU to only allow clients who have certificates signed by this subordinate certificate authority. So that may be sufficient for some use cases, but it's depending on how you manage X509 certificates in your environment, it may or may not be practical to use this approach. So we want to add a more flexible access control mechanism. So to this end, we're writing a general purpose authorization subsystem in QEMU. The initial implementation just maintains a simple access control list. So when a client connects to QEMU, it presents its client certificate. QEMU can then go and say, is this certificate in the access control list that I configured? And this access control list will just be a simple allow, deny, ordered list, and it will just go through the list until it finds a match and apply the policy that match is associated with. So that's a nice, simple approach. It doesn't rely on any external infrastructure. We'll be able to use that with VNC, character devices, migration, MBD, hopefully in the 2.8 release. That will be used with, if the service is using X509 certificates, it'll match against the distinguished name field in the certificate. For VNC only, if you're using the SASL authentication mechanism, it'll also be able to do a match against the SASL username. The slightly more advanced access control mechanism, people often have existing systems that they may use for controlling access. It's fairly common to have some kind of LDAP server where you maintain access control rules, or you might have some kind of SQL database somewhere where you want to manage this all centrally instead of configuring access control on each individual host. So we're creating a PAM plugin for QEMU. So you'll be able to tell QEMU to use the PAM object for access control, and that'll delegate to the PAM configuration file on the host. And if anyone knows anything about PAM, there's countless different backends for PAM that can authenticate against all manner of different things. So that'll give us a nice pluggable mechanism for integrating with arbitrary authentication systems that people may have deployed, whether they're open source or proprietary. QEMU won't care. It'll just be able to integrate with them with fairly minimal effort. And again, this is something I hope to get into the QEMU 2.8 release. And that's basically all that I wanted to talk about. It's quite a whirlwind tour of what I've been working on for the past year, and there's a hell of a lot of details that I've glossed over, not really explained. So as part of this work, I've been writing a lot of blog posts explaining this in more detail. So if anyone wants to follow up to read about this in detail, then if you go to this topic link, you'll find a series of blog posts titled QEMU Security, and you'll find all of the detailed information. And unrelated to this talk, there's a poll asking for your opinions about the KVM forum so that we can better plan what we do in future years. So if everyone can fill in the KVM forum poll, that'll be very helpful to the program committee. So that's it. If anyone's got any questions, there's a mic in the center there, so please feel free to ask or come and catch me afterwards. Oh, well, I guess I thoroughly confused everyone as there's no questions. So. Oh, we do have a volunteer.
I have a couple.
Okay.
So first of all, you're talking about getting secrets into QEMU for use in TLS. Is it possible to change a cert in use of a running?
It's not currently.
So you've got a really long-running QEMU
Yeah.
and your cert expires. Do you have to?
It's not currently possible, but it's something that we want to be able to support, and the new, more modular framework for dealing with TLS enables us to do that much, much more easily than would have been possible in the past. So it's something that is actually on the to-do list. It slipped my mind, but it's definitely something we want to be able to support for exactly the reason you say.
So my other question was possibly slightly off topic. You were talking about encryption in the guest. I'm wondering, is there any, or is it even feasible to virtualize a TPM, and would it be able to use any of this infrastructure? Would that be relevant?
There is already support in QEMU for doing pass-through of TPMs. So if you have a TPM on the host, you can pass that through to the guest. That's what existed in QEMU for, existed in QEMU for a while. There are patches proposed to enable you to expose a virtualized TPM to the guest, so you don't have to have a one-to-one mapping between a host and a guest TPM. So that would definitely be beneficial. If your guest disk encryption mechanism can make use of TPMs, then that would be something that would be useful in that context. But that's still there's quite active debate over the design of that. But I think eventually we'll get proper virtualized TPM supporting QEMU. It's just unclear exactly when.
There's also RNG, so that can help the guesting.
Yeah, on a slightly related topic, there's the VirtIO RNG driver, which allows you to inject entropy into the guest, or inject more specifically inject random bytes into the guest, which is helpful in various cryptographic primitives, especially during early boot when the guest probably doesn't have any entropy of its own.
Can you talk about the performance impact of encryption in general?
In a general way, I guess I can talk about it a little bit. I don't have any hard performance benchmarks to back up what I'll say, but with moderately recent CPUs, you've got native hardware support for doing AES encryption. So that helps reduce the burden of encryption compared to doing it all in software. Certainly the TLS support, the TLS libraries we're using certainly make use of the hardware encryption instructions where available. For the LUX encryption, I don't believe the primitives we're using for that will make use of hardware encryption, but that's certainly an area for further work. What I should have mentioned is that as part of this work, QEMU is now able to choose between either using the gcrypt library or the netl library, which are the two most commonly found C crypto libraries in Linux distributions.
Why, by the way? Why would you want to choose?
Because we link against GNU TLS, and depending on which version of GNU TLS you use, GNU TLS will link with either netl or gcrypt. So to avoid bringing in multiple crypto libraries, we want to link against the same crypto library that GNU TLS links against. But in the reality, for any modern OS, it's going to be using netl, or gcrypt is kind of on its way out, not as favored anymore. So I think we're basically out of time at this point. So if anyone's got any further questions, come and see me afterwards or use email. Thank you for your attention.